first edition conference, lopal'2018. We have a tremendous pleasure to greet in the second plenary session a great professor. He is he received his PhD from University Paris on interior point methods in 1987 and the habilitation thesis from University Paris in 2000. His main research topics are stochastic optimization, especially chance constraint optimization, conic optimization, and stochastic game theory, with application mainly to telecommunication networks and energy management. He has been a research engineer in Orange Labs for more than a decade. He is full professor at University Paris since 2001 and distinguished professor since 2016 in the same university. He published several papers in Canadian journals and conferences and is a member of some international journals and conferences worldwide. I'm so proud to present to all of you Professor Nisa, who will talk about on chance on probabilistic constraint games.
Thank you. So thank you very much, and thank you for attending this talk. First of all, I would like to thank the organizers, especially Latif Afia for his nice invitation. And I'm very happy to be here. This is I think my first time talking in my hometown. This is my hometown from this city. I grew up here. And we'll talk today on chance constraint games. So when Latif m'avait contacté pour, oh, sorry, go. Yeah, when Latif asked me to join the conference, I was thinking about some topic in stochastic optimization. Actually, my main topic at this moment is stochastic optimization, and especially chance constraint optimization. So I will give some definitions in a few minutes about this. But this is a bit the special topic in stochastic optimization itself. It's been basically, especially after a nice lunch and so I decided to propose some application of chance constraint. And the application is in game theory. So I'm not game theory guy, but a couple of years ago I had a postdoc student who did his thesis, his PhD in stochastic games. The stochastic games is a very big community. And we decided, I decided to see how to come up with the equilibrium, which is one of the main questions in game theory, by using chance constraints. So did I disconnect something? Oh, this was disconnected. Okay, so I will give some, probably will not go through all these topics, but I will start by introducing the chance constraints and the games and the main problem in games. And I will share with you some recent results we got on biometrics games. And each time I will talk about special, problem in this area in stochastic games. I will show how to compute the equilibrium. I will not show any numerical results. As when you characterize the equilibrium, you don't need to simulate, because when you simulate, you will find the equilibrium. You will show mathematically that it exists. So I don't have numerical results in this presentation, but you can find some in the papers I will present you at the end. So I will talk about these games for two kind of distributions. The more standard one, which is the Gaussian distribution. And I will show you some results on the elliptical distributions. And if we have some time, I will briefly present the distributionally robust games. Actually, the model for all these topics, even for people who are not very familiar with games, is how to compute the Nash equilibrium when you introduce the uncertainty in the game. So we saw some talks this morning where we talked about the uncertainty in data, for instance. And Philip also mentioned in his tutorial some uncertainty problems in optimization. And the objective here is to show what happens when we introduce the uncertainty in the matrices, the matrix of the game. How can we come up with the equilibrium? We can show that the equilibrium exists. So please feel free to interrupt me if you have any question or comment during the talk. So let me start by defining the chance constraints. So we have an optimization problem where we minimize Cx subject to some constraint, Gjx. And so we have X is the decision vector, we have deterministic constraints, and we have an index for this. So generally speaking, stochastic optimization problems are presented this way, where we minimize the expectation as the objective function, and we have the expectation in the constraints. Of course, sometimes we have only just the expectation as the objective function, and sometimes we have only the random parameters in the constraints. And so the expectation, is known as like it's a sort of mean, which means that when you have very high variability, it's better to use what we call chance constraints. So what is chance constraint? Is this constraint problem? We minimize Cx subject to this probability or chance constraints. So we have the probability of the constraint, which should be satisfied with a given threshold. So we fix the essaaidi, for instance, and we want that the constraints to be satisfied in 99%, for instance, which means that you take 5% risk in this case. Okay, so just a very brief illustration of chance constraint. This is very famous problem in stochastic optimization, which is the portfolio. So I guess many of you have already made this problem. So here the objective, we have a capital. We want to invest such that we want to maximize the revenue, the expected value. And we have the condition that the chance of losing no more than a given fraction should satisfy some threshold P. So this problem could be modeled this way. So we have the X, which is the fraction of the capital invested. We have the random variables, which correspond to the returns. And we have a fixed probability and the protection parameter for the protection against the losses. And this is the VAR, this is called VAR problem actually. This is the example of
adamı teslim etmiyorsun. Bize lazım. Fahri abilere söyle.
C-VAR. So probably you
Sen de Nevzat'la buluşmaya git. Oradan da yanımıza gelirsin. Nerede olduğumuzu biliyor musun?
Biliyorum da amca, ne demek bize lazım, ne demek teslim etmeyin?
Soru sormadan lazım diyorsam lazım.
Let me show again this insist and the chance constraints. So this is the problem I have just defined, and we have
Amcam her
some
zamanki
special
gibi
cases,
dayanamadı.
which
Sıktı.
means that we can
Benim
either
oradan
have
kendileri devam
the
ettiler.
random variables in the right-hand
Peki
side,
bizim amcam da aynı düşüncede mi abi?
and this is a bit easier to deal with actually.
Kendi
We
kafama
have
göre
very
iş
nice
yapmıyorum herhalde.
problems,
Al pasla
nice
boş boş
results, sorry.
konuşma.
So far in the literature.
Ne diyorsam onu yap.
And there is a little bit more complicated problem
Peki, İlyas
where
amca.
the uncertainty is in the left-hand side, which means you have the matrix cap
Abi,
side,
bence
which is
dönüyorsunuz.
random, and this is much more complicated. I need to deal with as the convexity issue. Actually, behind this probabilistic constraint is we need the convexity. And generally speaking, for the majority of the distributions, the convexity is not there. So then we need to do some convex approximations and all these things. So today I will not concentrate on this. We will just consider one chance constraint. And of course, if you are interested, we have some papers on this topic with joint probabilistic. This is called a joint probabilistic constraints. And problem could be much more complicated if you consider the dependence, for instance. But this is another story. We'll focus only on one chance constraint. And let me show you this very known result, which goes back to the early 70s and due to Prokopa. Prokopa is the famous guy who was very famous. This is a reference book called Stochastic Optimization. I strongly recommend this book for who wants to learn stochastic optimization and mainly mathematics behind this topic. So we consider the following chance constraint problem. And if psi are independent and follow normal distribution, then we can make this transformation. So we take the xi transpose x and we deduce the mean and we divide it by the standard deviation. Then we can transform the problem this way. And as I said, if k is greater than 1, then you have joint chance constraints. And if you have only one constraint, this problem could be transformed into this one, which is SOCP problem. This is called second order conic optimization problem. And you can see that this is very easy. Just replace the psi here and gx here, and you can come up with this formulation. So very, very simple way. So this is a convex optimization problem. F is the CDF, and F minus 1 is the inverse of the CDF. And for normal distribution, we know how to compute all these things. So this is what I will use in the main result I will present. So I will transform the chance constraint in the games into something deterministic equivalent, mainly the SOC. Okay, let's go back to the game now. My apologies for people who are familiar with these things, but I think it's nice to make some recall for the what is Nash Equilibrium. So this is very famous problem in games. It's called prisoner's dilemma. You have two prisoners, P1 and P2, and so they did some bad things. They were arrested by the police, and they have two strategies. They are separated. They are not in the same room. And they have two strategies. One is to confess, to see what happens, and the other one is to keep silent. And the same for the two players. And you can see here it's not the payoff, because this is not benefit, but this is years of jail. If P1, for instance, choose the strategy to confess, and the P2 choose the same thing, they will take 4 years jails. If P1 confess and P2 keep silent, then P1 1 year and 5 years for P2, and so on. And we can see here, if we take this strategy, for instance, P1 confess, then P2 will choose confess as well, because he will have 4 years jail instead of 5. And if you take P2 and if P2 chooses to confess, then P1 will confess as well, because he will have 4 instead of 5. In this case, 4 is the Nash Equilibrium. And as we have one strategy, this is called the pure strategy Nash Equilibrium of the game. You can see, for instance, that this is not the most interesting solution for both, as if they take silent and silent, they can have just 2 years jail. But Nash Equilibrium is not the best solution. It's the solution which gives the maximum payoff to players, regarding the fact that he cannot change his strategy unilaterally. I mean, he cannot change just by himself, otherwise he will get more years to jail for this problem. Okay, so it is well known in game theory, elementary game theory, that pure strategy Nash equilibrium does not always exist. So we can see this example, for instance, if you take right and left for P2 and top and down, you cannot find pure strategy Nash equilibrium here. However, we can have a mixed strategy Nash equilibrium, which is this one. So I want to show, we can compute Nash equilibrium in different ways. Generally speaking, it's nonlinear optimization, some complementarity problems, and some more complicated, I would say, nonlinear optimization stuff. So this is the Nash equilibrium. I would like to show you, because the notations in the game theory community are very different from the optimization community. We'll take this example and show you how we formulate the problem and define the Nash equilibrium before moving ahead to the problem we're interested in. Okay, so first let me show here the biometrics problem. So we have two players. And we have the two matrices, the payoff matrices of players 1 and 2. Player 1, payoff is A, and player 2, payoff is the matrix B, and x1, we denote x1 and x2, and y1 and y2, the mixed strategies for the two players respectively. We have this convex, constraint somehow. That's the non-negative constraints and the sum of xi and one equal 1. And the payoff, it can be written this way. And this is sort of bilinear optimization, for instance, as we have two variables x and y. And we can see that if we write this quadratic form, we get something like this from this example. So we keep this example, and now we use the notations for games. So here we have two players, so with the set I, 1 and 2. A1 has two strategies, T and D, and A2, the player 2, R and L. And the finite set, the finite action player set is called A, and this is set product of AIs. The payoff vector, we will denote it this way, R tilde 1 equal R tilde 1A, such that A belongs to cap A, and this is the payoff vector. You can see 1, 0, 0, 3 for player 1, and we have the same thing for player 2. We will call Xi the set of mixed strategies of player I, we will denote it by X1, which is set of 2, 1, such that we have this expression, and we have the same thing for the second player. And we have an example here, tau 2r equal y2, for instance, and tau 1 of t equal x1, and so on. So X is called the set of mixed strategies, and this is the set product of xi, and we denote the mixed strategy of player I by tau I. So here I did some manipulations just to show that why we write the problem this way. So here we have the payoff of player I, which is defined in this way, R1 tau, can be written this way. And if you develop this expression, you can find this. And the same thing for player 2. Actually, in the remaining of the presentation, I will just use this part. So just use the sum over the product of the strategies and the payoff. Okay, so now if we want to check the Nash equilibrium for the example we have at hand, we can compute R1 tau star, which is here will be R1 tau star and tau star 2. And if we take the different values, we can find that the R1 tau star equal 3 out of 4. And if we do the same thing for R1 tau 1 and tau star 2, then we find the same thing. So then we have this relation. And if we do the same thing for the second player, then we have the equality as well. And this is the definition somehow of the Nash equilibrium. So we can see here that this is the definition of Nash equilibrium. So the payoff of tau star, it should be greater or equal than the payoff for O tau 1 for the x1, and the same thing for the second player. And this is the Nash equilibrium, and we can see that in this example, it holds with equality. So it means we have the equality, we don't know which is more stronger than equality. Okay, now we will keep these notations. Now let's just generalize it to n players, and then, as I said, we move to the first part of the talk. So I, again, is the set of players. AI is the finite action set of player I, and we have the set I defined here. This is what we call an action profile. This is defined this way. The payoff of the player I and the payoff vector of player I. And this is the almost the last slide, the notations. Xi will be the set of mixed strategies. Cap X is the set of all mixed strategy profiles. And we will denote mixed strategy I of player I by tau I. And we'll write it this way, sorry. Oops. So tau minus I is the strategy profile for all the players except the player I. I mean, if you play yourself, you don't play against yourself. Just determine the strategy profile with the other players. Okay. So now to finish, though, for given strategy profile, we have this payoff, and this is what we will find in all the results where we will introduce the uncertainty. Now the payoff is known. We saw that the matrices are given, deterministic, and later we will suppose that these matrices are random variables. So strategy profile is said to be Nash equilibrium if we have this inequality. And as you may know that the Nash showed that there always exists a Nash equilibrium for this game. This is the result he got for the Nobel Prize, I think in the 50s. Right, so now we end up with the introduction part, and let's go through the biometrics game. So for biometrics chance constraint game, consists in, we suppose that the matrices A and B are random variables, which is a bit different compared to what is done in the stochastic community, stochastic game theory community, where they consider that the matrices are deterministic, they are given, and the transition from one state to another one is Markovian, this is stochastic. So this is different kind of games. And these games went back to the 70s. I think Charles has proposed a paper where he defined this kind of games. And since that time, as far as I know, there was no research or results published on this. I guess because at that time we didn't have this Conic optimization theory to come up with nice reformulations for the problem. And then they can fix it. Okay, so here we will define alpha 1 and alpha 2, the confidence levels of player 1 and 2. And we assume that alpha is known for all the players. So here we have the game where the information is complete. As you may know, I mean, even if you're not very familiar with games, that there are many kind of games where the finite games and finite games, complete information, incomplete information, dynamic games, repeated games, and so on. So here we suppose that we have the information is known to both players, and for given strategy pair XY, the random payoff is written this way. This is what we saw before, with the difference that A omega and B omega are random matrices. So, for given strategy pair X and Y, and given confidence level vector alpha, the payoff of 1, the player 1, is given here. So before we maximize this, when A is deterministic, now we transform the payoff into some chance constraint optimization problem, and here you can see the reference to chance constraints. Now the players, they will optimize with a chance constraint in their respective optimization problems. So here we have the supremum of U, such that the probability of the payoff is greater or equal than U, and this should be greater or equal than alpha 1. The same thing for the player 2. And then this is what we call chance constraint games. So So we assume that the distribution here of the entries is known to each player. The players know the distributions. Alpha is also known to the players, as I said. And this is what we call the complete information for chance constraint games. And non-cooperative means that each player has to maximize his payoff. And this is compared to the cooperative games where you have alliances, where the players make alliance and try to optimize according to the constraints of the alliance. Now to define the Nash equilibrium. For given alpha, we have a strategy pair x and y is said to be Nash equilibrium of chance constraint game if the following inequalities hold. And here you can see that we have something which is similar than before in the deterministic case, with the difference that we have alpha 1 here and alpha 2 for the second pair. It's the same scheme, but with the difference that the payoff matrices are random. Okay, so we suppose that the component of the matrix are independent normal random variables, where the mean and the variances are given here. And the same thing for B omega. And as I said, the independence is probably strong assumption in this case, but you will see that still, even with independent, the problem remains a bit difficult. Of course, as I said, we can have extensions to dependent random variables, but this is another story. Okay, so let's see if we take the quadratic form. This time with random matrix A omega, which follows normal distribution. So we take here normal distribution, which is very nice because thanks to the combination, when you have a random variable, the combination which is normally distributed, then combination of is also normal distribution. This is very important here. So we denote by U2 this the mean, and the standard deviation as sigma 2 squared. We introduce the variable z2n, which follows the standard normal distribution, and so far this is very simple things. And we have the quantile function of standard normal distribution. So now if we take the payoff function of for a pair of strategy of xy strategy, and for the confidence level alpha 1, then you can see that we start here with the payoff function, and we can come up with optimization problem this way, as I showed before. As we have normal distribution, then we can transform the problem into SOCP problem, SOCP type problem, and we look for the supremum of U such that U is less than this quantity, and the supremum is this one actually. And then we can write this expression here as the solution of this problem. And just by transforming the sigma into norm, we have this problem here. So as I said before, so we have chance constraint. We introduce the chance constraint. As we have random variables normally distributed, we come up with something like this. So we do not here, mu1 is this expression, and the sigma 1, the diagonal matrix with diagonal elements in this way. The record that only diagonal components are considered, and we do the same thing for the second player. Okay, so once we have these problems, then we have the convexity, and then we can show, of course, that we have the Nash equilibrium. Okay, let me show you now how we can come up with the Nash equilibrium by using nonlinear complementarity formulation. Are there any questions so far? Okay. It's a bit hard time after such nice lunch to go through the games and chance constraints. So please stop me if you have any questions so that I can make some breaks as well. Okay, so for fixed takes y, for fixed y, and alpha 1 in the 0, 5 1. Best response strategy of player 1 can be obtained by solving the convex quadratic optimization problem. So here we take the payoff we computed just before, and we add the constraints. So we have the sum of xi equal 1, the simplex constraints, and we have the non-negativity constraints. So in this case, the KKT conditions are necessary and sufficient conditions for getting the global maximum. And then we can write down the KKT conditions. Do you have a question? Sorry, do you have a question? No? Oh, no. Okay, so the best response of player 1 can be obtained by solving the KKT conditions. And here we have the KKT conditions. This is not very complicated. And we will do the same thing for the second player. So for x belongs to cap x and alpha 2 is 0, 5, 1. Notice that we cannot take alpha from 0 to 1. Otherwise we lose the convexity, because for less than 0.5 then you get 0 here. Then we have another quadratic optimization problem. We can apply also the KKT conditions for this problem. And to come up with the Nash equilibrium, we combine the KKT conditions for both. And by solving this, this nonlinear complementarity problem, where J zeta is defined this way, then we obtain the Nash equilibrium. So which means that if you have normal distribution, and together with the independence of the random variables, by solving this NCP problem, using, for instance, MATLAB or any other software, then you can come up with the Nash equilibrium. So we have the result in this theorem. So we consider the bimetrics gain defined by A and A omega and B omega, where all the components are independent and normally distributed, and all the components for the both matrices. And that zeta equal is the optimal solution of the NCP problem. Then the strategy part of x star, y star of zeta star is the Nash equilibrium of the chance constraint gain for given alpha between 0, 5 and 1 square. If and only if the zeta is solution of the NCP. I will not go through the proof, but you can find the proof of this theorem in the one of the papers I will show you at the end. So this was published, I think, in the Corner Journal. Okay, so this was the case for the normal distribution. Now we will move to something a bit complicated, I mean more general than normal distribution. So in stochastic community, actually, normal distribution is not really something random, because we know to do everything with normal distribution. We have the CDF, we have the inverse, we have the error function, we have everything. So now we will see something more general by looking to the elliptical distributions, which is the family of distribution, which where the normal distribution belongs to this family, and see how if we can come up in this case as well with the Nash equilibrium. So we consider the game where the payoff, which has a little bit of notations. This will remain the same, but you will see that later the notations are a bit different. So we consider the games where the payoff vector r tilde I of player I is a random vector. We have the sample space, a cup of omega, and we have the events defined in this set. The payoff of the player I is given by r tilde I, A, and omega. And similarly for an omega, the payoff is defined this way. This is what we have seen before. And we will see how we introduce the chance constraint problem in this way for this case. So for given strategy profile tau, player I can guarantee the following maximum payoff, and we have the same thing, which is written in a different way. Before it was all written the same. And here we consider the situation where player I is interested in the payoff that can be obtained with some risks. As I said, the players, they play with risk. So they are not guarantees that the constraint will be satisfied for any random event, which is impossible as we have an infinite number, but they take some risk. And they have to optimize some problem which looks like this one. For a given alpha I and for a given strategy tau, then the payoff optimization problem is defined this way. And in short, we will write it like this. So we assume again that the distribution of the payoff vector of each player is known to all players. Alpha is also known to the players. Here we have more larger interval, which is 0, 1. And still we have the non-cooperative game with complete information. Now we will define this new notion in the games, which is called the best response. So the set of best response strategies is given by this set. This is BRI alpha I tau minus I, and defined it this way. And for a given alpha, tau star is Nash equilibrium if for all the players the following inequality hold. This is what we said before, have already seen before. And also if tau star belongs to the set of best response, then we have Nash equilibrium as well. So first we will try to get the explicit form as we did before of the chance constraint problem. Let me recall again, so I repeat to show this, just to keep it in mind. And we will show that Nash equilibrium exists by using the Kakutani fixed point theorem to come up with this result. This is what Nash equilibrium used to find his result, and this is of course used very, very intensively for this kind of games. So we have again, this is the finite games with finite number of players and strategies. So Kakutani is the more suitable. Okay, let me say a few words about the elliptical distributions. We assume that the payoff follows a multivariate elliptical symmetric distribution with two parameters, mu I and sigma I. So the mu I corresponds to the location parameter, and sigma corresponds to the scale matrix, which is supposed to be positive definite. We consider also some generator functions in elliptical distributions. I will not talk about today about these generic functions, which leads to some dependence to the size of the for distinguishing different classes, actually, because we have different classes in elliptical distributions. But here we suppose we have just class 1 because we have this quadratic form which gives us one random variable at the end. So some famous elliptically symmetric distributions are normal distribution. We have just seen the T distribution, the student, Cauchy, Laplace, and logistic. Okay, so we'll try to do exactly the same thing as before, but as I said, this is the case for univariate symmetric, elliptically symmetric distributions. So introduce again some notations. I'm sorry, there are many notations, but the problem is different at each time. But again, just keep in mind that we have the payoff function with random variables which are distributed according to given distributions, and we want to show a Nash equilibrium. So here Ri follows univariate elliptically symmetric distributions. This is very important actually for this kind of distributions. If you take some exotic distributions, let's say hyper exponential distributions, for instance, you cannot apply this kind of techniques. Anyway, so we have the norm, it can be written this way, and again we introduce Zi, which is the variable which follows univariate spherically symmetric distribution with parameters 0 and 1. It's like the standard normal distribution. Notice that we call it spherically, what is dimension 1? But this is the name is given because sphere of 1 is not really sphere. Anyway, so we do the same thing as before. We take the payoff function and we just replace by as we did before, and then we come up with something which looks like this one. Looks like this one. And you can see this is a bit different than the than for normal distribution. So here we have some, different terms. The scheme is almost the same, but let's see what we will need as tools to show the Nash equilibrium in this case. So for this, we will define the power set. This is called Px of the set X, the set of mixed strategies, and we define the valued map J from X to Px, such that we have J tau is the set of all the best responses for all the players. And tau is a fixed point of set value map J if tau belongs to the J tau. And the fixed point of J is the Nash equilibrium. So let me just recall Kakutani fixed point theorem. How much time is there? Okay, so Kakutani fixed point theorem can be used to show that the existence of fixed point of map J. And the conditions for Kakutani fixed point are X is non-empty, convex, and compact subset of finite dimensional Euclidean space. We need the convexity and we need some continuity. We have the three conditions, then we have the fixed point, and then we have the Nash equilibrium. So we will start by showing that to come up with the convexity of the best response set, we need the concavity of the payoff function. And to show that the payoff function is concave, we can notice that the norm is convex, and F1 is 1, that is the one type is 0, which means that we need to take
الذي نسي في معظم 2017. صحيح أن العوائد الأمريكية ارتفعت لكن لم نرى ارتفاعا كبيرا في الدولار الأمريكي وهذا الأمر.
Okay, then we have this result, and so we can show that we have Nash equilibrium for elliptical distribution. This is the theorem, and we can find the Okay, so let me show how to come up with by using the best response, the convex problems, how we can compute the Nash equilibrium in this case. So again, we take the payoff function with the related constraints, and this time we will use some Lagrangian duality. So Philip talks this morning about this technique. This is very common. Then we have some Lagrange stuff and come up with the dual of the problem P and strong duality rule for primary pairs, and then we just put all the players of the problems and we maximize the sum and with the private and the dual constraints. So sorry, just go clear about this, and then we have this theorem where we prove that the Nash equilibrium, we can take the solution of this global mathematical optimization problem. Then this one, then we can show that this is Nash equilibrium. And you have the proof in the paper, which is under review for Jota. So, just before finishing, I don't have enough time to go into the details, but I will leave the slides. If you want more details, so please just send me an email and you can show me where you find these results. I just briefly want to show you that in the case where when the distribution is not known, which is particularly the case in the
تشاهدون في حلقة هذا الأسبوع من برنامج عين على فلسطين ترتيبات اقتصادية جديدة على طاولة المجلس الوطني الفلسطيني في دورته 23. نتائج متباينة للشركات المدرجة في الربع الأول ومؤشر القدس يخسر 10 نقاط. ورئيس صندوق الاستثمار يكشف الإسلامية العربية عن مفاوضات مع شركات عالمية مرشحة لتصنيع حقل الغاز قبالة سواحل غزة. تابعونا في الأوقات التالية.
in this case, how can we come up with some
هذا
robust
البرنامج
solution
برعاية
just by
صندوق
considering
الاستثمار
part
الفلسطيني
of the information
نستثمر
about
لمستقبل
the
أبنائنا.
random events. In this case,
والشركة
we can
العربية
use what we call
الفلسطينية
distributionally
للاستثمار
robust games. And
يقودنا
distributionally
التميز.
robust games
وبنك
consist
القدس
in constructing the uncertainty set,
يشاكس
we call it here DI,
يحاوره
and
ويناقش
the
قرارات
chance constraint game problem
يدخل إلى
becomes like
كواليس
this way.
المؤسسة.
Which means this, let me take an example. If you know, for instance, the expectation and the standard deviation, then you can consider all the distributions which have the same two first moments and come up with
هذا
an
البرنامج
uncertainty.
برعاية دار
Then you
الأركان
look for the worst case in this, for this uncertainty set. And this problem is written like this. You look for the supremum of C and such that the infimum of all the distributions defined in the case such that this constraint is not zero. And here again we find the chance constraint but in different contexts, different issues. So I don't have time to go into details, but just want to show you that if we take this case for instance, which is the case where we know the first two moments. Let me just check for this. Yeah. And then you can see that if we do the same thing as before,
الفيدرالي يقرر سعر الفائدة اليوم والأصوات لا تتوقع أي جديد قبل
now we have the supremum for all the distributions. Then we can have something which looks like this one. This function
اقتصاد منطقة اليورو يتفاوت في الربع الأول والبطالة عند أقل مستوى لها في قرابة 10 سنوات.
وفي نتائج الشركات أبل تفاجأ الأسواق وتحقق نموا قياسيا في مبيعات الصين.
So all these results are published all the way to. Then you can find in the go fast to the. Here we have all the papers and there are also some ones on my
ارتفع الناتج المحلي الإجمالي لمنطقة اليورو في الربع الأول من هذا العام ب 14 نقطة مئوية وفقا للتوقعات بالمقارنة مع عام 2017 كان بلغ النمو 2.5% على أساس سنوي.
Thank you so much. I'm asking our guests if you have any question or comments. One question.
Yes, Philip, over there. He doesn't need. He can speak.
Just maybe a silly question. I'm sorry. Yeah, I need something when you say that each player knows the confidence parameter.
Yes.
Of all the other players.
Yes.
Is an assumption. What happens if it's not the case? Can you apply the
It's complicated problem. You have kind of games which are incomplete information, and you should look at the likelihood stuff on this. It's not the same. It's completely different topic. But this is, I think, this kind of the. As far as I know, I didn't see any papers so far. There are some applications in energy mainly. I mean, this I didn't talk about applications, but these kind of problems can be applied to energy markets, where if you have many countries or actors, for instance, and they want to find the equilibrium. Let's say, for instance, I think I saw some papers in the European market of energy, where the equilibrium is very important to find or to approximate. Because when you have competitors, of course, you don't have all the information which is available. You don't have complete information games. So this kind of techniques could be used actually to come up with the equilibrium in this case. Of course, this is starting. I mean, this is 2-3 years research work, and I think we can apply it in many other games, including in complete informations or infinite games. We have some work on infinite games. If you are interested, of course, I can send you the paper. But we can apply it to many other games. As far as you have this game, I mean, you can come up with the convexity of the best response set. Then you can prove the Nash equilibrium. By using Constraint, of course, in this case.
Any question? Last one.
صرح بالأمس قال إنه لا يمكن البقاء في الاتحاد الأوروبي لأن البقاء في الاتحاد الأوروبي يعني الموافقة على الاتفاقات التي يعقدها الاتحاد الأوروبي. أيضا بدون أن يكون هناك رأي لبريطانيا في تلك الاتفاقات، وقال بالتالي هناك هيمنة من قبل الاتحاد الأوروبي على ملف الجمارك وخاصة بريطانيا، وهذا غير مقبول. هو ينتقص موضوع السيادة وينتقص موضوع حقوق الكامل. حتى الآن هناك أكثر من وجهة نظر، لكن الغالب داخل الحكومة البريطانية حتى الآن الغالب داخل الحكومة البريطانية هو التوجه إلى انفصال أو خروج كامل ويكمل العلاقة مع الاتحاد الأوروبي بعد موضوع الخروج. هناك رغبة أوروبية واضحة جدا تتكرر ضرورة البقاء البريطاني داخل الاتحاد الجنوبي، وحتى أن حتى الفترة الانتقالية فترة سماح بريطانيا عن رأيها وبقيت في الاتحاد الجنوبي وفي سوق المشترك.
يعني اليوم هنالك عدة وجهات نظر اليوم حول هذا الموضوع. إذا كانت بريطانيا ستبقى في الاتحاد الأوروبي، نعم قد من الممكن أن تحط خياراتها الخارجية خارج الاتحاد الأوروبي كالتجارة مع دول أخرى، ولكن في نفس الوقت معظم الإيرادات التي تأتي لبريطانيا تأتي من يعني فكيف ينظر القانون بالنسبة لهذا الوضع؟
And in this case, we use it when agents want to cooperate. And my question is, if you use your robust strategies, it will be very complicated to develop software for this kind of but if I understood, it will be something very robust and very strong.
Yes, actually, I didn't have time to talk about distribution and robust, but all the problems we consider here, we can solve them. So we can, I didn't present, as I said, in numeric results, because when you show that the Nash Equilibrium exists, we don't need just to generate randomly, but for all the cases, for the polytopic, when we consider that the uncertainty set is polytop, or for known and unknown moments. When you know the moments, then you come up with something like SDP problem. And then SDP problem we can solve it in polynomial times. And we can use some interior point methods for solving this. Same thing for unknown moments. Then you can solve again some semi-definite optimization problem. If you use other distributional robust techniques, namely using scenarios, for example, I think people interested in applications are more attracted by using scenarios, taking the information from scenarios and constructing the uncertainty set. This is called data-driven distributionally robust optimization, and in this case you can just solve linear optimization. So prone to this, to this frame for game theory, we can come up with, you can compute the Nash Equilibrium. But for these cases, of course, if you take some complicated uncertainty sets, probably that will be complicated. But of course, this kind of techniques, and namely the distributional robust, is much more interesting than just robust optimization, because you can find also robust optimization where the uncertainty is in set, defined in set, or in interval, or without any random information in the uncertainty set. So this is less conservative than the general robust optimization.
Okay, I think that's the start of our demonstration. Thank you again for the